accuracy and precision are two important terms. For example, if 5 darts are thrown and all hit the bullseye, each throw is said to be accurate and precise. Accuracy is the degree of closeness of the measured value to the true or actual value. How close the darts land to the center of the bull's eye determines the accuracy of the throw. Precision is the degree of resolution of a measured value when the same quantity is measured with different devices. If all 5 darts land at the same point, then the throws are said to be precise. Take, for example, an object whose absolute length is 32.56 mm is measured using 2 different instruments. Using the first instrument with a resolution of 1 mm, we obtain the measurement as 32 mm. Let us call this measurement M1. Using the second instrument, with a resolution of 0.1 mm, we obtain the measured value as 32.5 mm. Let us call this M2. Here, M2 is more accurate as it is closer to the object's true value than M1. Also, M2 is more precise as the resolution of the instrument used is greater than that of the first one. Any quantity that is measured should be accurate and precise, especially in science and technology. In reality, however, measured values carry uncertainty. This uncertainty is called an error. Errors are classified as systematic errors and random errors. A systematic error is a unidirectional error. That is, it is either positive or negative. A systematic error can occur due to an imperfect instrument, a faulty measurement technique, or incorrect process of measurement. Errors may occur due to the use of an imperfect instrument for measurement. Such errors are known as instrumental error. For example, if the needle of a simple balance is skewed or bent, it always shows a weight that is more or less than the actual weight of the object being weighed. Errors may occur due to an imperfection in an experimental technique or procedure adopted while measuring. For example, keeping a thermometer under the armpit will not measure the body's exact temperature as the mercury bulb is exposed to external factors such as air in the room, humidity, etc. Errors may also occur due to an incorrect technique or procedure being followed while measuring values. Such errors are called personal errors. Parallax is one such error. While measuring the length of a line using a foot scale, if you tilt your head, the length measured will be shorter or longer by a millimeter or 2. Systematic errors can be minimized or eliminated by using a perfect measuring instrument and by improving the technique or procedure of measurement. Random errors are akin to what they are called random. These errors vary in terms of sign and size. That is, they can be either negative or positive, and the quantum of error varies in absolute terms. These errors can arise out of unpredictable situations, such as a sudden change in environmental conditions, voltage fluctuations, or mechanical vibrations in the experimental setup, etc. Random errors can be minimized or eliminated by ensuring that measurements are taken under stable conditions and using properly set up instruments. Another type of error is least count error. This can be associated with both systematic and random errors. Least count is the smallest value of measurement that can be measured using an instrument. All values are considered precise up to the least count of a measuring instrument. For example, if you are using a meter scale, its least count is 1 millimeter. Hence, any measurement error will be in multiples of millimeters, not less. In academic laboratories, the general equipment used to measure length is a vernier calipers and a screw gauge. The least count error in a vernier calipers is 0.01 centimeter and for a screw gauge is 0.001 centimeter. Least count error can be minimized or eliminated by using high precision instruments or improving experimental techniques. Another way to reduce such errors is to repeat the measurements and take the arithmetic mean to bring the measured value closer to the actual one. If n measurements are taken, say A1, A2, A3, A4, so on till An, then the final value will be taken as the arithmetic mean of these n measurements. In the absence of a true value of measurement, this arithmetic mean is treated as the true value. The magnitude of difference between the true value and each measured value of a quantity is called the absolute error of that measurement. It is denoted by mod delta A. Since an arithmetic mean is considered the true value, delta A1 is equal to A1 minus A mean. Delta A2 is equal to A2 minus A mean, and so on till delta An is equal to An minus A mean. Individual error, delta A, may be positive or negative. However, absolute error, mod delta A, is always positive. Mean absolute error is the arithmetic mean of absolute errors of all measurements. If we take a single measurement instead of n number of measurements, then the value of the measurement lies in the range A mean plus or minus delta A mean. This implies that any measurement of a physical quantity A is likely to lie between the values A mean minus delta A mean and A mean plus delta A mean. Instead of absolute error, we often use relative error. Relative error is the ratio of mean absolute error to mean value of the measurements. Relative error is denoted by delta A. When relative error is taken in terms of percentage, it is called percentage error. When a quantity is derived from more than one measured value, the error in the derived quantity may be a combination of errors in the values from which it is derived. For example, the volume of a cuboid is the product of its length, breadth, and height. If there is an error in measurement in length, breadth, and height, then the error in volume will reflect the combined effect of all three errors due to mathematical operations. Some common combination errors are error of a sum or a difference, error of a product or a quotient, or error in case of a measured quantity raised to a power. When two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. If two physical quantities have their measured values A and B, and mod delta A and mod delta B are their absolute errors, find the error delta C in the sum C is equal to A plus B. We have by addition C plus or minus delta C is equal to A plus or minus delta A plus, B plus or minus delta B. The maximum possible error is C. Delta C is equal to delta A plus delta B. For the difference C is equal to A minus B, we have C plus or minus delta C is equal to A plus or minus delta A minus B plus or minus delta B, which is equal to A minus B plus or minus delta A plus or minus delta B, or delta C is equal to plus or minus delta A plus or minus delta B. The maximum value of the error delta C is again delta A plus delta B. When two quantities are multiplied or divided, the relative error in the result is the sum of the relative errors in the multipliers. Suppose a measurement Z is equal to A into B, and the measured values of A and B are A plus or minus delta A and B plus or minus delta B. Then Z plus or minus delta Z is equal to A plus or minus delta A multiplied by B plus or minus delta B, or Z plus or minus delta Z is equal to AB plus or minus B delta A plus or minus A delta B plus or minus delta A delta B. Dividing left-hand side by Z and right-hand side by AB, we get 1 plus or minus delta Z by Z is equal to 1 plus or minus delta A by A, plus or minus delta B by B, plus or minus delta A by A into delta B by B. Since delta A and delta B are small, we shall ignore their product. Hence, the maximum relative error delta Z by Z is equal to delta A by A plus delta B by B. This holds true for division as well. The relative error in a physical quantity raised to the power k is k times the relative error in the individual quantity. If z is equal to a square, then delta z by z is equal to delta a by a plus delta A by A is equal to 2 into delta A by A. Hence, the relative error in A square is twice the error in A. In general, if Z is equal to A to the power P into B to the power Q divided by C to the power R, then delta Z by Z is equal to P into delta A by A plus Q into delta B by B plus R into delta C by C. Whenever we measure the length or weight of an object, we note the measurement in the form of numbers. Here's a brick. Let's measure its length. Observe that the length is between 15.4 centimeters and 15.5 centimeters. Since we are not sure, we can say that the length is approximately 15.45 centimeters. In this measurement, 1 and 5 in the whole part and 4 in the decimal part are certain, while the 5 in the decimal part is uncertain. This 5 is uncertain because this is an approximate value. The values of many measurements in real life are decimal numbers. Digits in decimal numbers can be categorized as certain and uncertain. The number of digits in a measurement which are certain plus one additional digit which is uncertain are together known as significant figures. There are rules to determine the significant figures in a given number. The first rule says that in any measurement, all non-zero digits are significant. For example, we weighed a bar of steel that measures around 62.45 kilograms. Here, all the digits are non-zero numbers. In this number, all the 4 digits are significant figures. The second rule says that in any measurement, all the digits, including zeros, are significant for a decimal number greater than 1. Here, we have the length of a water hose, which measures 6.407 meters. This number is greater than 1. There are 4 significant figures in this number. The third rule says that in any measurement, if the decimal number lies between 0 and 1, the zeros to the right of the decimal point, but left to the first non-zero digit, are non-significant figures. Consider any number. Say 0.006452. Observe that there are 2 zeros between the decimal point and the first non-zero digit, that is, 6. These zeros are non-significant figures. Hence, the significant figures in this number are 6, 4, 5, and 2. Therefore, the number of significant figures is 4. The fourth rule states that if the measurement is a whole number, then the case becomes ambiguous if there are zeros to the left of an understood decimal point, but to the right of a non-zero digit. To remove this ambiguity, the number should be reported in scientific notation. That is, a into 10 raised to power b. For example, let's take a number 2507000. This is a whole number. According to rule number 1, there are 7 significant digits in this number. However, in this number, there is an understood decimal point, which is usually not written. The rightmost non-zero digit in the number is 7. There are 3 zeros between the 7 and the understood decimal point. We can report this in scientific notation as 2.507 into 10 raised to power 6. Now, the number of significant figures in this number is 4, since 2.507 is greater than 1. The fifth rule says that in any measurement, all the final zeros in a decimal number obtained by rounding off a decimal to a given number of decimal places are significant. For example, let's take the number 9.8982. There are 5 significant figures in this number. Let's round off the number to 2 decimal places. The resultant number 9.90 has the digit 0. But this number is greater than 1. Therefore, 0 is also a significant number. The number of significant figures in this number is 3. Using the rules we just studied, decimal numbers can be rounded off to the required significant figures. There are certain rules to round off the uncertain digits in a given number. The rule by convention says that the preceding digit is raised by 1 if the insignificant digit to be dropped is more than 5, and is unchanged if the latter is less than 5. Here is an example. We will round off 8.917 to 3 significant figures. This number has non-zero digits and there are 4 significant figures. In the decimal place, we will round off 7, resulting in the number 8.92. Here is another example. Round off 7.9342 to 4 significant figures. This number has non-zero digits and there are 5 significant figures. In the decimal place, we will round off 2, resulting in the number 7.934 as the number to be dropped, which is 2 is less than 5. Now, consider 2 numbers 3.945 and 3.975. Let us round them off to 3 significant digits. In this case, the insignificant digit to be dropped is neither greater than nor less than, but is equal to 5 in both the given numbers. To do this, we have another convention. which states that if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. Thus, the answers are 3.94 and 3.98 for the rounded off numbers as shown. Here, the length can be written as 8.1 plus or minus 0.1 or 8.1 plus or minus 1.2%. And the breadth can be written as 5.1 plus or minus 0.1 or 5.1 plus or minus 2%. Hence, using the combination of errors rule, the area of the field calculated as the product of these two quantities would be 41.31 plus or minus 3.2% or 41.31 plus or minus 1.3 square meters. We can report this as 41 plus or minus 1 meter square. Here, 1 square meter is the error in the result. Thus, the result also has two significant digits, which is same as the original data. Rule number 2 says that the relative error of a value of a number specified to significant figures depends not only on n, but also on the number itself. If there are two quantities, say 10.01 meters and 80.5 meters, both carrying an error of 0.1 meter, then the relative error in 10.01 meters is plus or minus 1%, while the same for 80.5 meters is 0.12%. Another important point to remember with significant figures is that intermediate results in a multi-step calculation should be taken to an additional significant figure in every measurement than the number of digits in the least precise measurement. Consider a number, say 6.55. The reciprocal of 6.55 taken to the same number of significant digits, that is 3, is 0.152. However, the reciprocal of 0.152 is 6.58, which does not match the original data we had. Now, if we consider the reciprocal of 6.55 to 4 significant digits, we get 0.1527, the reciprocal of 0.1527, taken to 3 significant digits, is equal to 6.55, which is the original data again.